If we could see sound, we would see sound waves, and the waveform is the first thing we should talk about. Different timbres have different shapes. We'll talk about frequency and amplitude in a little bit, but for now we're just looking at sort of the shape of the sound waves. The shape of the sound wave really determines the timbre, and as you can see, the flute, the guitar, and the saxophone all have different shaped sound waves. One thing that I thought was surprising is that the guitar has more or less the most erratic shape of the three played at the same frequency, yet I kind of imagined that the guitar would have the smoothest shaped sound wave. Frequency is the rate of vibration, or the cycles per second. In the previous slide we looked at the cycles of the sound waves and we saw how the different shapes determine the timbre of the sound, but frequency really is dealing with the rate of repetition of those shapes, and it's important to note that frequency is related to pitch. Each time the frequency doubles, the pitch raises by 1 octave. So if we look at this sound wave that's at 110 hertz, we can see 2 cycles. 1, 2. So we have 2 different cycles in that. If we look at twice that frequency of 220 hertz, we can see 1, 2, 3, 4 cycles. If we look at the next, doubling again, we can see 8 cycles. The amplitude of the sound wave really is the energy of the sound wave, and we refer to that in decibels. And it's really related to the volume or loudness of the sound wave. We indicate 0 decibels as the threshold of human hearing and 120 decibels as the threshold of pain. Interesting to note, doubling the intensity of the sound pressure variations creates a gain of 3 decibels, but we don't perceive that as a doubling. What we kind of use as the doubling is 10 decibels. So 10 decibels increase gives a perceived doubling of the volume. So here you can see a sound wave, and when I double it, or increase it to 10 decibels, that's where you get the taller wave as opposed to the shorter wave for the softer volume. When you try to record digitally, essentially you're taking that analog sound wave information and converting it into digital information. So as you can see right here, the process of converting analog audio signal to binary digital information. Essentially, as sound waves are hitting the diaphragm of a mic, the microphone is moving in and out, and it transfers those movements into positive and negative electric flow. When that positive and negative electric flow hits the AD, or the analog to digital converter, it converts it into a series of 1s and 0s. Now, the quality of the digital recording is determined by the sampling rate and the bit depth, or the resolution. The sampling rate is the number of samples per second, and the standard sampling rate for CD quality is 44.1 kilohertz. So that means for CD quality, a sound wave is sampled 44,100 times per second. Bit depth is the number of bits used to define each sample, and essentially it's the detail of each sample. 16 bits is CD quality. That really determines the accuracy of the amplitude, as we'll see in just a minute. The more 1s and 0s to define each sample, the better the quality, but 16 is the standard for CD quality. Sampling rate impacts the frequency resolution of a digital recording. The Nyquist theorem states that the sampling rate must be twice the desired frequency. So if you think about the standard human hearing range of about 22 kilohertz, twice that is 44 kilohertz. So when Sony was developing CD technology and they were trying to come up with a standard sampling rate for CDs, they used the Nyquist theorem to double 22 kilohertz, or the range of human hearing, and that got them to 44,000 kilohertz. They added in a little extra to account for some error, and that's where they came up with the CD quality. Now this idea of the wagon wheel concept is that if you ever watch a car tire, say on a car commercial or just driving on the road, sometimes it can appear that although the tire is actually rotating this way, when it goes fast enough, it appears to rotate backwards, or kind of forwards and then backwards. And that kind of relates to the Nyquist theorem. So if things are sampled faster, then we wouldn't have that error. But if things are sampled a little slower, then we would get that kind of illusion of weird sound waves. So that's something just to be cognizant of. The resolution, or the bit depth, as I mentioned earlier, has an impact on the amplitude of a digital recording. Essentially, the useful dynamic range of speech and music is 40 to 105 decibels. So essentially, a 65 minus dB dynamic range. You can kind of do the math to figure that out. If you have a higher word length, or more ones and zeros to describe digital events, then you'll have a greater accuracy and greater dynamic range. So essentially, a 4-bit word, which would be pretty low quality in terms of digital recording, that would only give you 16 amplitude levels, or 16 slots on the y-axis to describe amplitude. And that relatively poor recording would only give you a 24 minus dB recording. Now you can see jumping up to 16-bit gives us a dramatic increase in the discrete amplitude levels, up to 65,536, and that gives us a significant increase in the dynamic range of 96 minus dB. Professionals often record at 24-bit, and that gives us another dramatic increase up to 16 million discrete amplitude levels and a higher dynamic range of 144 minus dB. Recording at higher resolution sampling rates has another dramatic impact on the file size. If we take a look at the first column here of CD quality, 44.1 kilohertz and 16-bit, in stereo gives us about 10 megabytes per minute. If we start recording at higher qualities, let's say we're in a professional studio recording at 192 kilohertz and 24-bit, we're talking about 66 megabytes per minute of stereo audio. And if you think about multi-track recording in Pro Tools or other audio software, those files can get really big really fast. When we export a file to a WAV or an AIFF or an MP3, and our end purpose is to maybe get it up on the internet, or if we're using a handheld recorder to record audio, we have to be really aware of file size. WAV and AIFFs are full quality files. WAVs are native to Windows, AIFF are native to Mac, but both platforms read both files now. As you saw in the previous slide, these are going to be about 10 megabytes per minute of stereo audio. MP3s are going to be about 1/10 the size. You will lose some quality, but this is really best for publishing to the internet. You'll have about 1 megabyte per minute of MP3 stereo audio. As you can see down here at the bottom, MP3 at a decent quality, if you're recording to a handheld recorder, with typically there's a 1 gig SD card included, you have about 17 hours of recording, and that's very ample. However, if you're recording at CD quality, you only have an hour and a half of recording time. So if you do buy a portable handheld recorder, I suggest going with a higher memory card. I recently purchased a reasonably priced 16 gig card. I tend to record our concerts at stereo CD quality, and that gives me 24 hours of recording time. So I can just set record at the beginning of the concert, let the concert get recorded in full without any edits, no pauses, and then I can edit it later without any worry.